We're going to continue with section 3.7, the section with applied max-min problems. We did one problem in class on Friday. We're going to continue now. So a rancher wishes to fence off 3 sides of a rectangular pasture adjacent to the river. So 3 sides of the pasture, 3 sides of the rectangle are going to have fence, and the 4th side is going to be the bank of the river itself. That way the cattle can just go over to the river and drink, and the river will keep them from getting away, presumably. So she has 1,000 meters of fencing, and you're supposed to find the dimensions of the largest pasture in terms of area that she can enclose. So step 1, we're going to draw ourselves a picture. It's going to be as if we were looking down from the sky. So here's the river. And so here are the 2 river banks, one side and the other side. We're looking down from the sky, and here's the pasture that she's going to enclose. It's going to be a rectangular pasture. As I said, 3 sides of the pasture are going to be fenced, and the 4th side is going to be the river itself. That was step 1. Step 2, let's define some variables. What we have control over is the length and the width of this field. So let's go ahead and call this, how about we call this x, and we call this y. So 2 sides of length y and 1 side of length x. Of course, the river bank is also length x. And we also have to define area, which is the thing we're trying to maximize. So this doesn't have to be fancy. A equals area will be just fine. We could write let A be area. Step 3, we're already on step 3. So remember, if we don't start writing step 1, step 2, step 3, and a bunch of instructions, this takes a lot less time and a lot less space. So step 3, write a formula for area in terms of the variables we defined. So this time, A equals length times the width, x times y. We don't really know which one of those is the length and which one is the width, but there we go. Now, here we run into a problem that we didn't in the problem that we worked on Friday. Once we had the function to this point, we basically had it in terms of one single variable. This time we have 2. So I'm going to call this step was step 3a. So this was step 3, you'll recall, where we come up with a formula for the thing we're trying to maximize or minimize in terms of our other variables. That gives us a clue as to what variables to define. If you have more than one variable, you need to get down to one variable. You need to eliminate one variable. So what we're going to do is take a look and see if we can find something that connects x and y. So this is like step 3b. If you have more than one independent variable, eliminate all but one. So this time we have 2 independent variables, x and y. We have to get rid of one. To do that, we're going to look back at the problem. So the problem, we're going to look for something that connects x and y. Well, we haven't used this piece of information that we have 1,000 meters of fencing yet. Let's go ahead and use that now. We know we have 1,000 meters of fencing for this side and this side and this side. So let's write that down. Y plus x plus another y equals 1,000. In other words, x plus 2y equals 1,000. And so I can go ahead and solve for x in terms of y. So x equals 1,000 minus 2y. This is a step we didn't have to take in the previous problem, but we do have to take here because we had too many variables, too many independent variables when we wrote down our formula, in this case, for area. So x equals 2y. Let's go ahead and plug this back in where we see an x up here. So a equals x times, and we're going to replace, we're going to replace the x with this. So x is 1,000 minus 2y. So that was the 1,000 minus 2y. We're going to go ahead and write the y. We can multiply this together. So 1,000 y minus 2y squared. And now we have a in terms of just one variable, just in terms of y. So if you have more than one independent variable, when you get to step 3, do step 3b, get down to one independent variable. That's all we are set up to handle right now. So we have our formula now in terms of one variable. Let's go ahead and write our interval. Well, the smallest y can be is 0. So remember, the question is, do we allow 0 or not? In this course, I'm going to say, go ahead and allow it. It'll make our computations easier to do. So if we have y equals 0, basically we've used all 1,000 meters of fencing for x, and it just runs straight along the edge of the bank. So those poor cows are balanced precariously on the riverbank, and if they take one step in the wrong direction, they're going to fall in. So the smallest that y can be is 0. What's the biggest y can be? Notice there are two sides of length y. If we don't, the bigger y gets, the smaller x gets. If x goes all the way down to 0, then y is going to be 500. One way you can see that is if you set x equals 0 up here, then 2y is equal to 1,000, y is equal to 500. Or you can just look at your picture. The smaller x gets, the bigger y gets. We could just, if x is equal to 1, well, let's say x is equal to 2, then we have 499 feet going down, and then 2 feet over, and then 499 feet going up. We can set x all the way to 0, and then we have 500 feet, 500 feet. And again, those poor cows are trapped between 2 layers of fencing. So the biggest y can be is 500. So now we have our formula, 1,000y minus 2y squared. We also have our interval. Let's go ahead and solve our applied max-min problem. Our max-min problem, that's what we've been setting up in steps, well, this was step 4, in steps 1 through 4. So let's go. So step 5 is to solve our applied max-min problem. So let's go ahead and take our derivative. A prime of y equals 1,000 minus 4y. Derivative of 2y squared is 4y. We'll set a prime equal to 0. So 1,000 minus 4y equals 0. Y equals 250. Let's go ahead and test both endpoints and this point into our original function. So here's y, here's a. We can put in y equals 0, y equals 500. Those are our two endpoints, and the 250. If we plug in 0, we get 0. We knew we were going to get 0. If y is 0, this field doesn't come out from the river at all. It's just going to have 0 area. 500, same thing. We have 2 layers of fencing right up against each other. That doesn't enclose any area, so that's 0. If we put in 250, we end up with 1,000 times 250 minus 2 times 250. Oh, I see I'm probably off the screen right now. So let's just go ahead and see if we can work that out. So that's 250,000 divided by 2. So it looks like it is 125,000, I guess. If I've made a mistake, you'll have to forgive me, but I think that's right. So of the 3 of these, it looks to me like this is the biggest one. That's what we're trying to do. We want to go ahead and reread the problem. Find the dimensions of the pasture, so its length and its width. Let's go back over here. Well, right now we know its width. We know what y is. So the width is 250 meters. And to get the length, we can just go ahead and plug y equals 250 in over here. So we end up with x plus 2 times 250 equals 1,000. Solving for x, we get x equals 500 meters. And we made sure that we answered actually the question of the problem, which is not how big is the field. I mean, its area is 125,000 meters squared, I think. Again, you can double check me on that. But that's not what we were asked. We were asked for the dimensions, and here they are.